This guy?
Hey y'all, so last time we looked at parametric equations and we learned how to graph them. Today we're going to look a little bit more closely at the equations and not so much the graphs to answer a few questions. For instance, we're going to be able to go from a set of parametric equations to a single rectangular equation and vice versa. Also, we're going to look at how to find when an object is at a particular coordinate. For instance, I might ask the question, at what time is an object at the x-intercept, or any sort of related question. So those are the kinds of things we're going to look at today. First, let me bring up a problem that we worked on in the last video. So last class we looked at this particular set of parametric equations and we made a table and we used a domain restriction to graph the set of parametric equations. Now clearly this graph is parabolic and we could use the points that we found to determine a quadratic function equation for y in terms of x. However, it might be nice to be able to come up with this rectangular form of the equation without having to make a table or a graph. And to do this, we're going to use a technique called eliminating the parameter. So eliminating the parameter goes a little something like this. First, you're going to look at your set of parametric equations, and in this particular set we will solve for t in terms of x. There might be some problems where you need to solve for t in terms of y, depending on the parametric equations, but in this particular one we are going to solve for t in terms of x. In other words, we're going to rearrange this equation so that it's t equals. So I'm just going to rewrite that out to the side here. X equals negative 2t, and I'm going to solve for t. So to do that I need to divide by negative 2, so I get x over negative 2 equals t, or we might rewrite this as negative 1/2 x. So here what I've done is I've solved for t in terms of one of the variables. After you do that, you're going to take that expression and you're going to substitute it into the other equation. So in this case, since I isolated t in terms of x, I'm going to take this expression and substitute it into t in the second equation. This technique of eliminating parameters is very similar to what you do when you solve a system of equations using substitution. You're doing very similar steps here. So when I plug in negative 1/2 x into t up here, what I get is y equals 4 times negative 1/2 x squared minus 4. And then I can simplify this. So negative 1/2 squared is 1/4. X squared is just x squared. 4 times 1/4. Well, here, let me break this down. So 4 times 1/4 x squared. 4 times a fourth is just 1. So this ends up simplifying to be just x squared minus 4. Now you might think back to the set of parametric equations when we graphed them. Let me pull that up real quick. There was a restriction on the domain, right? We had negative 1 all the way to 2 as our t values. And the way that ended up playing out is you can see we have this implicit restriction on the x values to where the smallest x value here is negative 2 and the largest x value is positive 2. Or I'm sorry, the smallest x value is negative 4 and the largest x value is positive 2. So we also want to account for that when we convert to when we convert to rectangular form, because if we were to go ahead and just sketch this by itself, that would just be that parabola, but it would be the entire parabola, right? So we want to also convert the domain in terms of t to the domain that we need in terms of x. So we've already solved for t in terms of x here. So all we need to do is just substitute this into the t for the domain. So this is going to be kind of a separate thing that we'll do. And so let me rewrite the domain as -1 less than or equal to t less than or equal to 2. And I'm going to make the substitution right here. I'm going to rewrite t as -1/2 x, which will give me -1 less than or equal to -1/2 x is less than or equal to 2. And from here, I'm just going to try to isolate x by using the normal steps that you would use if you were just solving an inequality like this, which is we just want to multiply everything by -2. Now, one thing to remember is when you have an inequality, if you multiply the whole thing by a negative, that does flip the sign, and in the case of a compound inequality like this, it is going to flip both signs. So this will turn out to be, let's see, times -2. I'll just write this out just to make this as clear as possible. Multiply everything by -2, and that's going to give me 2. Flip the sign is going to be greater than or equal to x greater than or equal to -4. So the domain in rectangular form will be -4 less than or equal to x is less than or equal to 2. And you can see that should match up with the original domain we had in parametric form. And you can see from this graph that that's absolutely right, that the x values do go from -4 to 2. So we have our answer here, which is y equals x squared minus 4 with a domain restriction of x being in between and including -4 and 2. So this is one example where we took a set of parametric equations and used the eliminating the parameter technique to rewrite it in rectangular form, which by that I mean in terms of y and x. Now, what if you wanted to go backwards? Let's say I had a rectangular equation like this, and I wanted to convert that into parametric form. Well, the only way that that's even possible is if a parameter is defined for you, because depending on how t is defined, there may be multiple different ways to write a set of parametric equations. And in fact, what that does, one way to think about it is, let's say we had this one, right, where we're basically just tracing out this parabola. You could imagine a lot of different scenarios here where, let's say the object is traveling right to left. Well, that would have a different parameter, a different definition for t than if the object was traveling from left to right. So right there you have two different potential opportunities for a set of parametric equations. But it goes way beyond that, because the object that's moving can move at different speeds potentially. So in other words, if I want the object to move really quickly, I will set the parameter to be equal to something different than if I want it to move slowly. So usually in these kinds of problems, when I'm asking you to go from rectangular to parametric, I will typically be giving you a parameter, defining the parameter up front so that your answer is unique. So let's go through an example where I would give you a parameter and a single equation. You give me and the rectangular equation, and we'll work towards the parametric equations. So let's say we have a rectangular equation like y equals 1 minus x squared, and I want to convert that to a set of parametric equations. Again, what I'm trying to find is an equation for x and an equation for y that would produce the same graph as long as they're both in terms of t. Now, as I was saying before, I can't do that until I have a parameter defined. So let's say that I wanted to convert this using the parameter t equals 1 minus x. Okay, so again, like this would have to be given to you in order for there to be a unique solution. Otherwise, there would be infinitely many solutions. If you could just pick any parameter you'd want, the easiest way to go about doing would just say, hey, t is x, and then you plug it in and you're basically done. But okay, so let's come up with an equation for x and an equation for y, both in terms of t, that would have the same graph as this guy, but where the parameter is defined like this. So the first thing you want to do is solve that parametric equation here for x. And that will give you your x equation right away. So if I have t is equal to 1 minus x, and I add x to both sides, it's going to give me t plus x equals 1. And then if I subtract t from both sides, move this up a little bit, I get x equals 1 minus t. So right away, there's one of my parametric equations. You're just basically rewriting the one that's given so that you have it solved in terms of the coordinate that you're interested in. Once you have that first one, you are going to substitute that into the rectangular equation. So we know x is 1 minus t, so we can substitute 1 minus t for x in here. So let's go ahead and do that. Y equals 1 minus t squared. So you can see, okay, well this really technically is a parametric equation here, but let's go ahead and simplify this a bit. Now 1 minus t squared is going to be 1 minus 2t plus, not 2, but t squared. You'd have to multiply that out using FOIL to get there, but that's what that would be. And then so you have 1 minus that, which is really like 1 plus the opposite of all these terms. So that would be 1 minus 1 is 0. So that goes away. And then so you have minus a negative 2t is 2t, minus a t squared is minus t squared. So now we've got an equation for x and an equation for y. And so we have our set of parametric equations. So we've got x equals 1 minus t and y equals 2t minus t squared. And that would be a set of parametric equations that would trace out the exact same graph as this one up top. So now we've seen how to convert a set of parametric equations to a single rectangular one, including the domain conversion. And we also looked at how to go from a rectangular equation that has a given parameter and go and convert that to a set of parametric equations. Now the next thing we're going to look at is how to find when an object's position that's defined using parametric equations is at a specific point. So for instance, like when is the object at 2, 3 or something like that. So let me show you one example of how to do that. The key thing here is that you have to solve for a t value that satisfies both the x and y coordinate, depending on what the question's asking. So let's say we have an object whose position is defined using the parametric equations x equals sine of pi over 2t and y equals 4t squared minus 5t. So this expression describes what's going on with the x coordinate in terms of time, and this expression explains what's going on with the y coordinate in terms of the time. So the question here that I'm going to ask is find when, so like in other words, find a t value, find when the object passes through the point 0, 6, if it even does. In this case it does, but let's go through how you would actually find that t value. So the key here is that we need to find a t value that will not only make x equal to 0, but we need y to also equal 6. So what we're going to have to do is essentially solve two different equations, one for where x is 0 and one for where y is 6. We're going to solve both of them, and since they both have to be satisfied, we are going to look for t values that appear in both solution sets. So it's not enough to just like it's possible to find a t value, for instance, that would make x 0 that makes y something else. In other words, like you could have a bunch of y-intercepts here. Like you could say 0, 6 is a point, 0, something else, And we don't really care about those other ones in the context of this problem. We only want to find when is x 0 and y 6. So the way I'm going to set this up is I'm going to say exactly that. If I want to find when this is going to occur, I'm going to say I'm really trying to solve this compound statement of x equals 0 and y equals 6. Okay, and I'm looking for a t value. Now in this case, I'm going to actually solve these separately because there's they're two totally different functions. So the solving process is a little different. So I'm not going to do them simultaneously. So let's start with the x one. So x is equal to sine of pi over 2 t. And I want to know when is that 0. So when is sine of an angle measure 0? Well, we might want to pull up our handy unit circle here. So we're trying to find where sine is 0. And if you recall, sine is going to refer to the y coordinate around the unit circle. So we can see that sine is 0 here and it's 0 over here. So it's 0 at 0 radians, pi radians, 2 pi, 3 pi, 4 pi, etc. So let's just show, I thought I had my cursor on there. So you can see right here it's 0, so we can say 0 radians, then pi radians, the y value is also 0, and you can keep going around. So like 2 pi, 3 pi, 4 pi. What you'll notice is that this occurs at every iteration of pi. So let's go ahead and pull that down. And so we know that sine is going to equal 0 at every integer of pi times pi. So we're going to say that that angle measure, pi over 2t, is going to equal pi times every integer. All right. So this is the angle measure. Sine of an angle measure is 0. That angle measure is going to be 0 pi, 1 pi, 2 pi, 3 pi, all the negatives as well. So from here, I need to solve for t. So I'm going to start by just multiplying both sides by 2. And that will give me pi t equals 2 pi n. And then I'll divide both sides by pi. So let's see what happens there. So that's going to be kind of nice. It's going to eliminate the pi's on both sides. So I get t equals 2n. Okay. So if you're thinking about like all of the values of t that would ensure that x is 0, it's going to be 2 times every integer that there is. So like for instance, let me just write it as a set here. Like if n is 0, you get 0. If n is 1, t is 2. So all these multiples of 2 essentially. So for each of these t values, x is 0. So what we know here, but kind of by thinking about this, is that we're going to have a bunch of y-intercepts, a bunch of coordinates where the x is 0 at time equals 0, time equals 2, 4, 6. And something else I didn't really account for here is that when I use n here, I'm saying any integer, and integers can be negative too. So I'm actually going to do plus or minus here because this could be like -1 times 2. -2 times 2, it should be -4. So a lot of solutions here. In fact, there's infinitely many. But this is not the whole story, right? Because this only shows us where x is 0. We need y to be 6 as well. So we're going to solve that equation separately. 4t squared minus 5t is equal to 6. So we've got this quadratic equation. Really hoping it's going to factor, but let's find out. If not, we'll just have to use that good old-fashioned quadratic formula. So let's see if I can come up with two numbers that multiply to give me -24. I'm going to do some scratch work out to the side here. -24, but add up to -5. And if you want some clarification on just how factoring works, come see me during the meet and I'll kind of go over this process a little bit more detail with you. But being that we're in pre-cal, I'm going to kind of assume that you remember how to do this. We've done some factoring already. But anyway, we can come up with two numbers that multiply to give me 24 and add up to -5. And that would be -8 and 3. So we can factor by grouping here, and we'll get 4t squared minus 8t plus 3t minus 6 equals 0. So in other words, I just split up that middle term. Now I'm going to do the actual grouping step where I'll factor out the GCF out of this first group and this group separately. So the GCF out of this first group is 4t. When I factor that out, I'm left with t minus 2. And the GCF of this second group is 3. So plus 3 times t minus 2. When you're doing the factoring by grouping, you always want to stop at this little stage right here and verify that these two things are the same, which they are. So that means we're doing this right. And therefore, our two factors are going to be t minus 2 and 4t plus 3. So that gives, we're going to have two solutions here, right? We're going to have a solution that's t equals 2 and a solution where t is, let's see, minus 3 divided by 4 would be negative 3/4. So because this is an AND statement, both have to be true. So we're looking for the t values that satisfy both. What this is basically saying is that there are two times where the y coordinate is 6, okay? But only one of those two times corresponds to x being 0. So you can kind of see where that's going to be. It's just going to be at this t equals 2. Right? That's the only value that satisfies this equation and this equation. So again, the key thing here is that the t value has to satisfy both. If there isn't like an overlapping value here, like if, let's say we got like t equals 3 here, or that'd be over here. Oh no, that's not over here. Yeah, let's say we had t equals 3 over here. Then there'd be no solution. You'd be able to answer this saying, oh, that's never going to happen. The object never passes through 0, 6 if there's not a time that is shared by both of those coordinate equations. So to answer this question, you would say, at what time is the object passing through 0, 6? The time is at t equals 2. Now this can get a little trickier. You know, you can see that the difficulty here is going to really depend on what functions you're given to solve. You know, if you're given a sinusoidal function, it may have been a little while since you thought about that. You know, if this was a polynomial function, you know, you'd have to factor and do all that good stuff. But let me show you one other type of problem here that's sort of similar to that one, where I'm not looking necessarily for when the object's at one particular point, but when it is in like a certain space, okay, on the plane. So let's say that we had you know, some object whose position is defined using these parametric equations: x equals t plus 1 and y equals t squared minus 7t plus 12. Let me make that a little clearer here. My webcam at home is not as good as the dot cam at school, so it's a little blurry here, but hopefully you can see that. Let me make that a little clearer. Plus. Okay, so let's say that the object's path is defined using this set of parametric equations, and I want to say, and here's the question: find when, again, we're looking for t values, find when the object is in quadrant 2. Okay, so in other words, who knows what this thing's doing, but I'm curious, like, when is it up over here? So the first thing to think about is, what are the conditions on the coordinates x and y for you to be in quadrant 2 anyway? Like, what has to be true about x if you're in quadrant 2? What has to be true about y when you're in quadrant 2? Well, when you're in quadrant 2, the x value is negative and the y value is positive. So we're going to use that to sort of set us up. Like in the last problem, we were given a very specific point that x had to be 0 and y had to be 6. Or here we're going to say, well, x just has to be negative and y just has to be positive. So these are the two sets of not equations here, but inequalities that we have to solve. And again, this is going to be an AND statement, a compound inequality that we need to solve. So once you understand sort of the, you know, how to set it up At this point, we're just going to be solving an inequality. So x is t plus 1. So if t plus 1 is less than 0, that means t must be less than negative 1. So before time is negative 1, the x value is negative. So that doesn't tell us anything about y. So that just means we're to the left of the y axis, in quadrants 2 or 3, as long as the time is less than negative 1. So when is y positive, right? When are we up here? Well, when t squared minus 7t plus 12 is greater than 0. So this is a polynomial, specifically a quadratic, but in the last unit, we learned how to solve polynomial inequalities. So to solve a polynomial inequality, first you find the zeros. Okay, so if I factor this, I get x minus 3 times x minus 4. This one's pretty straightforward, not too complicated. The numbers here are pretty small. And then so my zeros would be at positive 3 and positive 4. So the way to sort of check to see when is this polynomial going to be positive, I draw a little number line, I put my little zeros on there, and I create these partitions, right? I've got 3 partitions here. And I want to decide whether or not the function is going to be positive or negative. I'm just going to keep track by picking a representative from each interval and plugging it in, and really only caring about whether or not the whole thing's positive or negative. I don't care about the value necessarily, because all I'm really trying to do is figure out where the whole thing's positive. So I could pick a representative from this leftmost interval, let's say 0. 0 might be somewhere over here. If I plug that in, I get a negative times a negative, which is positive. So in this interval, that would satisfy this equation, or this inequality. Now let's go to the next interval, 3.5. If I plug in 3.5, I get a positive times a negative, which is negative. And then finally, if I pick some huge number like 100, I'm going to get a positive times a positive, which is positive. So there are 2 intervals that will satisfy this inequality, and that is when t is less than negative 3, and when, I should say, or, I'm going to be careful about that, or when t is greater than 4. Okay, now we've got like a crazy compound inequality here, because we're saying this statement and this statement. So when you have like these kind of embedded compound inequalities, I think the best thing to do is to sort of sketch out a little number line graph and look for where the solutions overlap. Because remember, we have to find the solutions that satisfy this and this. So even though like numbers bigger than 4 are going to satisfy this one, they're obviously not going to satisfy this one, right? Like if I pick 100, that's not less than negative 1. So 100 is not going to work. This whole interval is not going to work. But let me show you visually like how that would play out. I'm going to draw a number line here and really just put the key values that I really care about here. Negative 1. Oh, negative 3 would be before that. My bad. Oh wait, that should be positive 3. What am I doing? Where did that negative come from? So yeah, no, I'm right. Negative 1, 3, and 4. Okay, so I'm going to do these in different colors just to make it a little bit more obvious. Like I'll do this one in red, okay, and say that t is less than negative 1. Okay, so that's how that would look like on a number line graph. Open circle going to the left. And then I'll do this other one in this blue pen, although it kind of looks black on the way it's coming through on the video. That's going to be less than 3, okay, or greater than 4. All right, so there's all those numbers that, all the values that are in these intervals will satisfy the second inequality. So in order to satisfy an and inequality, both have to be true. In other words, the t values have to be less than negative 1, but also fall in this, this inequality. So that's going to happen where the 2 solution sets overlap. In other words, like right here, right? This is where you see the red one and the blue one overlapping. And so the overlap here is really occurring at t less than negative 1, all the times before negative 1. Because this is saying t, it could be less than 3, but you don't actually start getting less than negative 1 until you get that small, right? Like these for instance, like 0, 1, and 2 will satisfy this one, but not this one. But the values less than -1 will satisfy both of these inequalities. So the answer to the question, when is the object in quadrant 2? Well, it's in quadrant 2 anytime before t is -1. So that's it for today. Go ahead and start working on some of those problems in the practice problems, and have a great day.